our tutorial and about data heterogeneity analysis under dispersion shifts. And I'm Jiashuo from Tsinghua University, and it's the final year of my PhD. And unfortunately, my advisor Peng cannot join us because of some visa issues. And this tutorial is based on the joint work and materials with Jose, Tiffany, Bo, Jiajing, Hongfang, Tianyu, and Jiayun. And now let's begin. It's really a fast development of AI system recently, and people hope to use AI for all of their applications in real world. However, before we deploy our AI systems in practice, one key question is that whether the advanced AI system can generalize well in some wild scenario that they may face in practice. And to begin with, we'd like to share some interesting failure cases of AI systems and to demonstrate the risk of today's AI. And the first one is a sweeping robot that is stuck into a grid. Here I have a video. It's like it's an interesting example, and also another interesting example is an AI camera that mistakes the referee's ball head for the real football, and it keeps tracking the referee rather than the player. And here's a camera, a video of this. We can see that it keeps tracking the referee's head rather than focusing on the football or the player on the game. And also during COVID, many researchers and clinicians hope to use AI models to help people do some diagnosis and also to give some treatment suggestions to our patients. However, there are some papers finding that existing AI models, they have extremely high bias and risk when predicting COVID, and therefore they cannot be trusted in such high stakes area. And for example, according to this report, COVID predictors were found to be just picking up the text fund for prediction. And that is found from hospitals with more serious case loads became predictors of COVID risk. And this clearly demonstrates that the risk of AI systems should be considered before we really deploy them into real applications, because they can make mistakes easily. And also for auto driving, here's another interesting example where the AI system thinks that there's a person in front of it, and it keeps jamming on the brakes. And also the training data of self-driving is mainly some natural and common scenarios, but when using some rare cases, it may fail to generalize well. For example, in this case, it cannot recognize the road or something else. And to demonstrate these failure cases of AI systems, we really need to go back to the fundamental assumptions of machine learning, which we also know is the ID assumptions. And that is when the test distribution is quite different from the training one. The model may perform very poorly, and we refer to this problem as the out-of-distribution generalization problem. Actually, there are many model problems under shifts. For example, our model may have poor generalization performance, and also they may be unfair to some minority groups. And also they may be sensitive to some data perturbations. And all of this we refer to as the model problems under distribution shifts. And actually we find that these model problems are somewhat caused by some data problems. For example, there are distribution shifts, and also there are some latent subpopulation structures that we are unknown or we did not consider during our training phases, and therefore our model may be unfair to some minority groups. And also there may be some data corruptions that our models are sensitive to. All these are some data problems. And in this tutorial, we propose a more data-centric way to address distribution shifts. That is, if we can analyze the data problems better, we may be able to solve the model problems in a much easier way and in a much more efficient way. And the main scope of our tutorial is we are trying to analyze data heterogeneity to address the problems caused by distribution shifts from a systematical perspective. And here are three keywords, and the first one is data heterogeneity. And it refers to the complex nature of data. For example, our data may contain subpopulation structures. Maybe there are some hard samples or noisy samples, and even there are some different data generating process or different data types and sources. All of this we refer to as the data heterogeneity. For example, in modern machine learning, models are exactly based on heterogeneous data sources. Like in this figure, we collect data from different sources and we merge them together into our training data. And we just train our models using this training data. However, in this training data, we can see there are multiple environments and there are different Y game X distributions, and maybe data from different sources have different data size. But actually today, because of big data, even the minority group, we have plenty of data to analyze it. Therefore, for today's AI, there's opportunities and challenges of data heterogeneity. And the second keyword is distribution shifts. It means the complicated shift patterns in practice. Actually, there are two main sources of shifts. The first one is data corruption. It means that maybe our samples may be polluted or modified by someone. That is data corruption. And the second source is like subpopulation shifts. And it can be decomposed into X shifts with Y game X shifts. And here we'd like to provide more demonstrations of these two kinds of shifts. And actually, so far, humans are robust on all distributions. For example, given an image, we can easily tell its labels. But can we get a universally good model? And implicitly, this will actually focus on the covariant shift, like X shift, and its traditional focus of machine learning. On another hand, we expect Y game X shifts when there are actually unobserved factors. And that's the traditional focus of causal inference. But for Y game X shifts, this means that actually the prediction mechanism may change from one domain to another. And in such cases, we do not expect a single model to perform well under all distributions because the prediction mechanism changes. And this requires an application-specific understanding of distributional differences. And also the third keyword is systematic. And in this tutorial, we are trying to provide a system of view into the whole machine learning pipeline. And we specify 4 stages of the whole machine learning pipeline, including data collection, model training, model evaluation, and deployment. And in this tutorial, we would like to show how a better understanding of data heterogeneity could help in each of these 4 stages. And now is the outline of our tutorial. And the first part is a critical review of existing approaches, because there are also already so many methods or algorithms developed for distribution shifts. And this can be classified into 3 kinds. And the first one is distributionally robust optimization, and the second one is invariant learning, and the third one we refer to as some pre-trained really big models. Actually, the first two parts, they make some modeling assumptions, and the third one, they just scale up the model size and scale up their data to have a really large model. And now we come to the first one, distributionally robust optimization. And here we'd like to show some high-level ideas of what does DRO mean. And as we all know, in machine learning, we also use the empirical risk minimization. That's the first equation. We just optimize the average risk of in our training distribution. But for DRO methods, actually, we can see the objective is slightly different from the ERM, which tries to first find the worst case distribution in a predefined ball, which is lying around our training data, and then it minimizes the risk on the worst case. And for example, if our training distribution contains both older people and younger people, and for the distribution in this predefined set, it may consider different mixture ratios of young and old people. And the key steps of DRO involves like 2 stages. The first one is we are trying to define the set of distributions that we care about. And then we are trying to minimize the loss on the worst case. And we can see that actually the set is defined on some kind of distance metric, and we can use different kinds of metric to define this kind of ball. And now we'll show 2 metrics that are commonly used in DRO. And the first one is F divergence. And generally, F divergence, it only considers the density ratio between 2 distributions, and it penalizes the ratio from 1. And here we can see its formulations. F is a convex function with F1 equals 0, which means that if the 2 distributions have the same density ratio and they are the same, and F divergence equals 0. But when the density ratio is away from 1, like these 2 sides, which means that these 2 distributions are quite different, and then the F divergence will also blow up. And this is the F divergence. It's about reweighting the data. And here we showcase an intuitive example. If in our training distribution, we have maybe 70% of older people and 30% of younger people. And after reweighting, we may have equal ratio of these 2 groups. And also they may look like this, and even they may look like this. And it's about to reweight the data and in some degree, to some degree, and then we pick the worst case to optimize. And then we move on to another commonly used metric called Watson distance. Also, it's known as the optimal transport distance or the Earth moving distance. And consider if we want to change this distribution Q to distribution P, we may want to move the mass from one distribution to another, and there's a minimum cost to transport Q from P. And Watson distance, it just calculates this kind of minimum cost, like some optimal transportation cost. And different from F divergence, which only considers the density, actually from here we can see that the Watson distance it considers the data geometry itself. And for example, here we also use our 2 examples to showcase what the distributions in the Watson set may look like. And here's the training distribution, also the same as the previous example. And for Watson ball, it changes the age of some points from 60 years old to maybe 45 years old. And the distribution may look like this. It may just like create some new points, like ghost points in our distribution. And also it may look like this. And here we provide a comparison between F divergence and Watson distance. And for Watson distance, it goes in this horizontal direction, which is to move samples from one distribution to another. But for F divergence, it compares in this vertical direction. It's like we are trying to capture the difference between the density ratios rather than the sample points. From this, we could again understand why the distance metric is quite important in DRO, because actually different distance capture different kind of shapes. And on DRO, we really need to understand what kind of shapes we are caring about, and we need to pick the appropriate distance metric to build such kind of set. And since it's quite important and it's an active dimension in DRO research to come up with even better distribution set that aims to capture more realistic shapes that may occur in practice. For example, we may do not need to focus on all queries, but only some of them. Like in our age example, maybe we only care about the variable age, and then we can use like marginal DRO. And also we may use different metrics like MMD distance for kernel methods. And also in recent research of DRO, there are people try to combine different metrics together to have like a whole or general DRO methods like holistic DRO and unified DRO. And here we just provide many of these papers here, and if you are interested in this line of research, you may refer to them after our tutorial, and I've already shared our slides in our Slack channel. And however, given the rich literatures in DRO, there has not been a commonly used code base for people to compare DRO methods or for try to use DRO method in practice. And actually, we really need such kind of code base because we need an easy use of DRO methods in practice. And for this reason, we developed a Python package for DRO, which currently integrates 12 typical DRO methods and is an easy to use code base for DRO. And now let's summarize what DRO is doing. In the modeling stage, it carefully chooses some kind of distribution set, and it picks the worst case distribution in that set, and it optimizes the worst case one. And the goal is to do well on real distribution sheets. But between the modeling and the goal, there is an implicit assumption. That is, we really hope the worst case distribution could capture the real shifts. Then again, this leads to a question whether this assumption holds in practice, and our answer is probably not. In our recent paper, we built 7 settings on real-world tabular datasets with quite different shift patterns, and we test most of the typical DRO methods on our benchmark, and where we use linear models like logistic regression and SVM. And from our results, we find that actually DRO methods, they do not show significant improvements over simple ERM models like logistic regression or SVM. And this is quite surprising because DRO methods, they are actually designed for distribution shifts, but why they do not actually work in practice. And then we try to analyze some reasons behind this. And the first reason we call is the over-transmissing of the worst case. And here we just calculate the optimal in-distribution accuracy for each distribution. It means that maybe for one distribution P, we just fit our model on it, and then we report the accuracy on it. It's an ID setting. And here we test different kinds of models like logistic regression, SVM, neural networks, and some tree-based methods. And for example, for the source domain, we find the in-distribution accuracy is quite high, about 80%. And also, we examine 50 target domains, and we find, and here we report its quantile, and we find the in-distribution accuracy is also very high. However, for the worst case distribution produced by DRO methods, we could see that in this red box, even the optimal in-distribution accuracy is super low. And this means that the worst case distribution is too conservative for us to fit a model, or it's quite hard to learn a right prediction model. And this problem we refer to as the over-transmissing problem of the worst case distribution. And the second reason may be the mismatch between the worst case and the real target domains. Because here we use like 50 target domains. It's really a huge amount of target domains. And here we calculate another metric we call the transfer accuracy from worst to target. It means that we fix the worst case distribution and we train our method on it. And then we test this model on the other 50 target domains. If this transfer accuracy is high, it means that the two distributions are aligned well with each other. Otherwise, it means that there's a mismatch between them. And here we just plot like a violin plot of these transfer accuracies. We find that actually the transfer accuracy is quite low. And it means that the worst case distribution actually is not aligned with 50 target domains. Even when we have 50 target domains, it cannot align well with the worst one, which means that it's too conservative, and maybe we should not try to use this kind of methods in practice, even if they have some beautiful theoretical properties. And here's an introduction of DRO methods. And given that it's quite hard to pick the set of distributions, how can we do better? What if we were given a set of environments that we may care about? And for example, if we have known that there are different styles of images like cartoon, natural, and art. How could we generalize our model to another domain like sketch? And compared with DRO, where we only have one training distribution, we may think about having more information about the potential distribution shifts. This may give us more information and make it better for modeling. Based on this setting, invariant learning is proposed, which assumes multiple training domains, like from here P1 to PK. And the goal is to generalize to some new domains like Q. And also this setting is also called like domain generalization. And now we move on to the second method called invariant learning. And to generalize to new distributions, the high-level idea for invariant learning is to learn some kind of invariant prediction mechanisms across given environments. And the goal is to generalize to some new environments. And also there's an implicit assumption that does not really appear in many of the invariant learning papers. It's about, actually we assume that the true invariant mechanism can be learned with given heterogeneous data. And we'd like to introduce some typical invariant learning methods. And the first one is invariant causal prediction. And the high-level idea is to find a subset of covariates with an invariant relationship to our outcome label Y across different environments. And here we use a quite simple causal graph to demonstrate what does the subset of covariates mean. And here, the goal of our prediction is to predict whether I will be late for school. And there are so many factors may affect this outcome, like traffic accidents, heavy rain, maybe get up late or traffic jam. And here's a causal graph to model this process. And the invariant predictors refers to this red block. It contains two variables. The first one is getting up late, and the second one is traffic jam. And we can see from this figure, these two variables are the direct causes of this outcome label Y. That means that even the other variables changes, their effects can be blocked by these two kinds of variables. And as long as we know the value of these two variables, we can predict the outcome Y in a reliable way, because they do not change and they are the direct causes. And also beyond this raw feature level, another quite famous work is called the invariant risk minimization. And it assumes the existence of feature phi-x, such as the relationship between phi-x to y is invariant across environments. And then it tries to learn such kind of invariant feature. And here we use another example on image classification, where we would like to classify between cows and camels. But actually, for most of the images, we could imagine that most of the cows appear on grass, and also most of the camels may appear on sand, and that's like a spurious correlation between the animals and the background. And if we just use ERM to learn such classifier, maybe our model will simply use background to predict the animal. But for invariant learning, the goal is to use only the animal features for prediction rather than the background. And here's the objective function of IRM. And we can see that it requires, here the phi is the representation layer and the W is the classification parameters. And the constraint requires that we hope the optimal classification parameter stays the same across all the invariants, which is captured by this kind of invariance. And this is an invariance penalty. And for practical optimization, it can be relaxed to this kind of invariance penalty. Is like we just want to align the gradients of our classification parameters across all the environments. And by doing this, we may align. It's like we can contrast between these two kinds of environments, and our model will not use the background for prediction, and it will learn to only use animals for prediction. And this is invariant risk minimization. And also to make it clear, we can formally define the invariance assumption here. For example, we require the conditional distribution of all invariants to be the same as the first invariance property, like Py given phi stays the same across all invariants. However, you may think that even for some random noise variables that are independent with y, this property also holds. But they are non-informative at all, and we cannot use them for prediction. To overcome this, we need the second assumption of property. It's called sufficiency property. It means that we should use phi to predict y, and such kind of phi is called the causal invariant predictor. It means that phi star cannot be some random noises, and it should consider some information for us to predict y. And also to make it clear, here we can construct an invariant set containing all the invariant predictors. And our goal is to try to find the maximal invariant predictor by maximizing the mutual information between this kind of representation with target y. And this is called the maximal invariant predictor. And the maximal is about the maximal mutual information. And also there are many other works on invariant learning, and they propose some slightly different invariance assumptions, and they develop some corresponding invariance penalties for the model to learn some invariant representations or relationships. And I also put many references here, and if you are interested in it, you can refer to them together later. And now we make a summary of these two kinds of methods, DRO methods and invariant learning methods, about their data heterogeneity and also what kind of assumptions they make. For DRO methods, the heterogeneity is like a predefined set of distributions near the training distribution. And the assumption is that the worst case one could guarantee the generalization. And for invariant learning, the data heterogeneity is like a predefined set of environments. It's some predefined heterogeneity. And the assumption is that we can learn the true invariance from our predefined data. But also the key question is, do these assumptions work in practice or do they hold in practice? Also not really. And here from a famous benchmark named Dominbat, and we find that actually both RM and DRM methods, they cannot beat ERM on image datasets. And here we just briefly introduce some kind of methods, and we will leave their problems in our third part, and where we will introduce our research to improve those methods. And now let's move on to the third kind of methods, and we call the pre-trained big models. And they just scale up the model size and they scale up data for better generalization ability. And here we only take the CLIP model as an example because there are so many large models recently. And for CLIP model, researchers have more in-depth analysis and understand why it can generalize well under different kinds of distributions. And here the CLIP model is a pre-trained model, and the overall architecture of CLIP is like the left figure. It has two encoders, the text encoder and also the image encoder. And it uses some pairwise data points. Each contains one image and one caption. And during pre-training, CLIP tries to align the embedding of image and the caption. And during test time, for the given image, we can convert the labels into some context, and we can compare the similarity between the context embedding and also the image embedding. And we just pick the most similar one as its label. And it's a rather simple zero shot classification. However, CLIP models is found to be really robust to natural distribution shifts. And researchers find that actually it's more robust to compare with previous pre-trained models on many ImageNet variants. And actually one big difference between CLIP training and standard ImageNet training is the training data. While ImageNet is trained only on 1 million images from one source, and the labels are obtained by human labelers, CLIP is trained on 400 million image and text pairs from a bunch of sources across all the internet. And the scale of this data is possible because there exists lots of images with captions on our internet, and it does not need any human labelers. And one advantage of clip is its ability to easily use much larger data sets than ImageNet data sets, which needs human labelers. And we just discussed how the training data is really different from the standard way, but there are also other differences in training. And how do we know which one is the cause for its robustness? For example, clip training seems to contain additional language supervision. Like for each image, we do not only have its label, but we also have a long text to describe it. And maybe this caption is the key for its robustness. And the researchers from in this paper, they perform careful experiments where they list difference between clips and the standard pre-trained models, and they try to rule out all of these reasons except for the training distribution. And for example, they trained the models with a clip objective, but on ImageNet with image captions rather than class labels, which did not have good performance as the original clip. This suggests that the language supervision by itself is not the source of robustness. And extensive experiments also show that it is the skill of the image data, not language supervision, that is a cause of the robustness of clip. And so a natural question is that, is this an end? And are all of our problems solved once we train a model on data from all of the internet? And our answer is no. And I'll present like two answers. And the first one is that if we just add in more data, it does not mean we can get better robustness. And this is revealed by this paper. And for example, in the plot here, the authors of this work, they look to see if you get additional robustness by training clip on a mixture of two pre-training data sets compared to just one. And actually, they surprisingly find that the robustness is exactly between those two pre-trained data sets individually. So it does not look like the right thing to do is just we train a model on all of the data sets. And then you might hope that there may be one best data source that is just the best, and we should only train our model on that data set. But that's not always the case. Also in this paper, the authors show that there's no one best data source for all of the ImageNet variants. That means that if we want to achieve best performance on one data set, you may have to train your model on the corresponding best data source. But there's not only one best data source. And it seems like choosing the best training data is pretty tricky. And also the second reason is that sometimes we may need some specialized data, and they are super expensive. And so previously we talked about scaling up data by collecting and curating these huge data sets, about 400 million images. But these huge data sets have led to many really great advances in machine learning and also in large language models. However, there are still important applications that require more specialized data, like some healthcare applications or some finance scenarios. For example, some diseases require diagnostic tests in order to be detected, and those diagnostic tests can be very rare and they are super expensive. And also, if we are trying to understand the effect of a medical treatment on healthcare outcome, or the effect of a policy intervention on economic outcomes, getting this data requires a treatment or policy to be deployed, and the cost of deployment can be quite high. And also, if we are hoping to understand the long-term healthcare treatment effects or some long-term economic outcomes, the time cost is also quite high. And therefore, in many really important settings, we really do need to get some specialized data rather than just collecting data from the whole internet. And so to recap, we look at two existing approaches to get models to perform well across shifts. The first one is like for DRO and inference learning, and they make some clear assumptions about shifts. But the limitation is that current methods actually they do not exactly check whether their assumptions hold in practice, and also from many empirical studies, they do not consistently provide robustness under many real distribution shifts. And the second way is like we just scale up our data and also our model size. And the strength is that it works well to improve robustness to many real shifts patterns. But the limitation is that it cannot be used in many high-stakes areas where the data is too costly to collect. And so the question is whether we can do better. And here our suggestion is that actually we should not just make assumptions, or we should not just scale up data models. Instead, we need to first understand our application and understand our data. Then we need to make appropriate modeling assumptions. And also, even if we need more data, we have to understand where we need data, especially when the data is costly, and we first need to identify what kind of data is most helpful for our to collect. And here are some takeaways of our first part. It's like empirical current methods like DRO and inference learning. They do not provide large gains. And also these methods make assumptions about relationships between data distributions, but they actually do not check them. And also we must model real distribution shifts rather than some hypothetical ones in an application specific manner. And for large pre-trained models, we also need a better understanding of data distribution. And in response, in this tutorial, we propose carefully understanding the real distribution shift patterns in each application and also in different stages of the whole machine learning pipeline. And I think we have some time for our part 2, and it's not long. Maybe we can finish this and then go to break. And the second part is we move on to a shift to an inductive research philosophy. And here we'd like to first demonstrate what is the inductive and the deductive way of research. And also we have some motivated examples to show the need for an inductive way to deal with shifts. And here we borrow a figure from Christopher's and Holmes' slides, and we use this figure to demonstrate the difference between inductive way and deductive way. And the key difference is the starting points. For induction, we start at this observation facts. And that is, we observe some facts, and then we try to have some theories, or we try to discover some laws that can explain these facts. However, for the deductive way, we start at some ideal hypothesis. And for example, in DRO and inference learning, we just make some assumptions that we think people will believe in. And then we come up with corresponding methods. However, they do not really check whether the assumptions hold in practice. And therefore, we need for a combination of inductive way and deductive way. And here's a motivated example. And the task here is an income prediction task. And we train the XGBoost model on data from California, and we test them on Puerto Rico. And we find actually there's a huge performance drop, like about 10%. And then we may have, we can use some method to identify the covariance regions and to try to understand why our model drops. And we find that actually for female people with that are highly educated and their work types are some really good jobs like managers, financial people, or entertainments. Actually, for this kind of people, our model performs really poorly on Puerto Rico. And after we have this understanding of our model failure case, we can think that why this happens. And one potential reason is that actually the official language in California and Puerto Rico are different. Because in California, people speak English, but in Puerto Rico, the official language is Spanish. And as for income prediction, we can imagine that if one can work for some international companies, he may earn much more. He may earn a lot more, and therefore language feature is actually really important for income prediction and exactly for this kind of transfer. But however, in the original data sets, they do not include the language feature, and then we just add back this language feature, and we find this simple intervention is worth a lot, and the shape disappears a lot. And this is what we call an inductive way, because we begin with an understanding of distribution shift patterns before we make some modeling assumptions. And we find that it can solve the problem in a much more efficient way. And also, this method not only works for one method, but also it works for all methods. Here we test like 20 models with different model configurations. And in this plot, each point represents one model with one model configuration. And if we compare red points with blue points, the red points is the performance after we add back the language feature. We can see that actually the transfer performance improves a lot. And this actually shows the power of this kind of inductive way. And for the tools in these examples, we'll introduce in our third part. And that is why we need an inductive way of research, because if not, we may we may have some false empirical discoveries. And actually, here's a very interesting example. The accuracy underlying phenomena is a really famous paper, and also there are many follow-ups to show this linear trends between the in-distribution accuracy and the out-of-distribution accuracy. It means that actually, if our model achieves better performance on our training data, it can generalize well even on the target data. And actually, when we first saw this phenomena, we wonder whether it's because they are doing experiments only on the image data set. Because on image data sets, there's mainly X shapes, like covariance shapes. And then we repeat the same experiment settings on tabular data, where YQ-X shapes dominate. And we find that in the right figure, actually, we cannot observe. And actually, in the right figure, we can see that actually we do not observe such kind of linear trends. It means that this phenomena only holds maybe under strong covariance shifts. And also for the left figures are the linear trend found on many kinds of image data sets. However, on our recent benchmark, we find that the same when YQ-X shapes dominates, we cannot see such linear trends. However, when there's mainly X shapes in our last figure, and we also show that kind of linear trends. It means that actually we should not claim any empirical observations before we really understand the shift pattern, because in that way we may have some false discoveries. Like this accuracy on the line, it may only hold under X shapes, but in the original paper they claim that for all kinds of shapes there's a linear trend. And also the second reason is that if we do not have an inductive way, and if we do not understand our shift pattern, the empirical value of methods designed for shifts is limited. Recall that here the DRL methods and ERM, they do not actually outperform ERM on image data, and also in our recent work we find that DRL methods, they do not outperform ERM on tabular data, where we compare DRL methods with many ERM models like logistic regression neural networks, SVM, and also many tree-based methods. Actually, we find that even for very different shift patterns, DRL methods, they are designed for distributed shifts, but they cannot perform better. And also, the third reason is that if we can have a better understanding, we can design or select some targeted methods that may work more efficiently. And here we just showcase two examples that may also that also appears in our third part. That is, if we have a better understanding of shapes, we can even greatly enhance the performance of DRO methods. For example, for this X shapes, we can identify which variable has the most strength of shifts, and we can only perturb those kind of variables rather than all the variables. And we find that for some of our selected variables, like Watson's and DRO and also marginal DRO, they can even outperform some tree-based method, and there's a huge improvement in their performance. And also it holds for YG max shifts. We can identify some kind of variables that is the most strongly correlated with the shifts, and then we can only perturb such kind of variable, and this leads to a more efficient improvement. And the last reason is that if so, we can obtain better improvements. And this comes back to our main scope in this tutorial. It's like we are trying to analyze data heterogeneity first to address the problem caused by shifts from a systematic perspective. And maybe we can have a break now, and maybe for like 15 minutes, and then we'll come to our third part, is the towards heterogeneity over machine learning, where we would like to discuss how we can combine this understanding into each of the 4 stages of the whole machine learning pipeline. Yeah.